Hello dear students, welcome you back for lecture number 4 on the topic system of particles and rotational motion. So far in this topic we were able to understand what is translational motion, rotational motion. We were also able to study the concept of center of mass and torque. So in today's class we are going to study moment of inertia, a very easy concept. So what exactly is moment of inertia? This inertia for rotational motion is called as moment of inertia. So all of you are familiar with the word inertia. You might have come across this word in the laws of motion topic. Okay, so you can split this moment of inertia into two words, moment and inertia. Moment is the rotational effect, which is nothing but the torque, and inertia is the property of a body by virtue of which it tries to maintain the same state of rest or uniform motion. It's an application of the Newton's first law. I hope. What is inertia? Inertia is a measure of mass, okay, or it is the resistance to the motion or in the state of rest. So inertia for rotational motion is called as moment of inertia. This inertia you have studied in Newton's laws of motion. Now this same concept of inertia, if we apply for rotational motion, then it is called as moment of inertia. So moment of inertia, to understand moment of inertia, just try to understand if this is a fixed axis, and in that axis if there is one mass attached to it and it is rotating about this fixed axis, x-axis. Let me do this and let this distance be r, okay, and it is rotating in this axis. So moment of inertia is given by I, and how do you measure it? I equals to mr square. Remember, moment of inertia is a scalar quantity. It's a scalar quantity. Since inertia is a scalar quantity, how you measure it? SI unit will be what? Kilogram meter square. Can you write the dimensional formula of this? M1, L2 and T0. Got it? So whatever inertia we have studied in Newton's laws of motion, if that inertia is applied for rotating body, then it is called as moment of inertia. So how do you put that into words? Moment of inertia can be defined as, it is given by I is equal to mr square. Suppose there are n number of bodies. If there is one more body here which is rotating in this direction, one more body here and rotating in m1, m2, m3. So moment of inertia can be written as I equals to m1 r1 square plus m2 r2 square plus so on up to mn rn square. So in generalized form you can write I is equal to summation of mi ri the whole square, where I equals to 1 and 2. So where I can be 1 2 3 4 5 anything. So moment of inertia is not applicable for just one mass system. If suppose there is one fixed axis, and for that fixed axis there are n number of masses connected, or a whole body, and if you consider an individual particle, so moment of inertia can be also defined as the sum of product of the masses of each particle and square of the distance between them. Now very important here is, when I consider the distance this r, I am considering the perpendicular distance. Okay, it doesn't mean ki you can take this as moment of inertia. Suppose if you want to find moment of inertia about this axis, don't consider this as r. For that axis, the perpendicular distance is called as moment of inertia. Got it? So in generalized form you can write for n number of masses mi ri square, where I can be equals to 1 up to any terms n. Now how can we define moment of inertia? Shall I erase this? So, definition: moment of inertia of a body is defined as sum of product of mass of each particle and square of perpendicular distance. This is very important. Square of perpendicular distance from the axis of rotation. So this is exact definition of moment of inertia. Moment of inertia of a body about an axis, you write about an axis. You are expected to write this definition in the exam. So moment of inertia of a body about an axis is defined as sum of product of summation. It can be any terms. Sum of product of whose product masses and square of the perpendicular distance from the axis of rotation. This is called as moment of inertia. Got it? It's a scalar quantity measured in kilogram meter square. Got it? Now let us understand how does that value came. I is equal to mr square. We'll go back to our linear motion concept. Now all of you know F is equal to ma. This is a Newton's law, right? Where m was a measure of mass, and measure of mass is nothing but inertia. Got it? Now this is my equation 1. I'll multiply r on both sides of equation 1. So when I multiply r, this will become rf ma into r. Got it? Now what is this a? A is acceleration, but here body is rotating, so which acceleration to be considered? Definitely an angular acceleration. And what is the relation between acceleration and angular acceleration? R alpha. Got it? Just like velocity, R omega. So acceleration will be what? R alpha. This is in linear, this is in rotational. So R into F ma, instead of a, right here R alpha into R. All of you are understanding what did I do here? Instead of a, I just multiplied R alpha and this R. So R into F equals to m alpha R square. So this will be what? R omega square. So this will be m into alpha R square. Got it? So have you understood? So I'll just rearrange the terms from here. Rf equals to mr square into alpha. Got it? Now what is R cross F? Let us understand this is a cross product. R into F. The other class we have studied R cross F is nothing but torque, which is a vector quantity. Mr square. What is mr square? Just now I told you mr square is nothing but mr square is moment of inertia. So shall I write mr square as I, and this is alpha, which is again a vector quantity. So compare this equation with F is equal to ma, where F is a linear force, torque is the rotational force. M is the mass, and mass is a measure of inertia. Here I is also a inertia, but inertia of rotational motion. So by this way I got I equals to mr square. Are you understanding? How did I got that? I equals to mr square. So is it easy to understand? Yes. So now this moment of inertia depends upon, on what factors it depends? First it depends upon size and shape of the body. Shape of body. Second thing, it depends upon the axis of rotation. And third thing, it depends upon the perpendicular distance r from axis of rotation. From axis of rotation. Have you understood? Got it? Okay. So have you understood this equation? This is just to know you how this value of I came as mr square. Just take F is equal to ma, multiply R on both sides. Instead of A, substitute for angular acceleration. A can be written as alpha R. So R into R will become R square, and this ma. So rearrange the terms mr square and alpha. So compare this. What is R cross F? Torque. What is mr square? I. And this. Compare with this. Have you understood? Okay. So now we'll do some problems on moment of inertia as soon as possible, so that we will understand the concept of angular momentum also. Now suppose, first question, find moment of inertia of a body along x coordinate of a square. Suppose this is a square, this is the axis of rotation. Here there is one mass kept m, and m. Let this distance be r, let this distance be r. Since it is a square, all axes are same. So now find the moment of inertia of this body which is rotating along this axis. This axis is Ix axis. Got it? Now find moment of inertia. What is, according to the definition, moment of inertia of a system of particle is defined as sum of product of masses into square of the distance. Right? So what is I moment of inertia about this axis? You calculate for this first, m. Now this is axis of rotation, this perpendicular distance. So this is r, so this will become r by 2. This will be r by 2, and this will be also r by 2, as well as this also will be r by 2. The total distance is r from this axis. This distance will be what? R by 2. It is passing from the center of mass. So here will be what? Mr square by 2. Yes or no? Plus here also this will be what? Mr square by 2, Mr square by 2, and Mr square by 2. So how many times Mr square by 2? 4 times. Yes or no? Find Mr square by 2, Mr square by 2, Mr square by 2, and Mr square by 2. How many times? 4 times. So Ixx will be what? Mr square of this will be Mr square. This is whole square. So this will become 4. Got it? Mr square. Don't square m, into 4. So 4 gets cancelled. So Ix will be what? Mr square. Show with a vector quantity. Have you understood? A very easy problem. Okay. So this way you should find moment of inertia. A very simple formula. You have to just take the axis of rotation and just multiply the mass and with the distance. Got it? Try to solve one more problem. Suppose there is a triangle, or equilateral triangle. Okay, all of you know what are the properties of equilateral triangle, and there is one mass kept here, m. Equilateral triangle means equal distance from all sides, equal sides, AN. The axis of rotation is passing from this line, Ixx. Okay, you are going to find moment of inertia of this system of particle. Let this distance be A. Okay, now moment of inertia of this particle will be what? The axis is passing from here, so r will be what? 0. So m into 0 will be 0. Then find moment of inertia of this particle plus mr square, sorry, this is A, no? So A square plus, now find moment of inertia of this particle. Have you understood this particle? This is A, so this also will be A. Equilateral triangle, right? I did not tell you all sides are equal. So from this side, from this axis, you have to just see the axis, and from that axis where is the mass kept? At distance A. Now this mass is here. So some of the students may take this as the distance A. No. What is moment of inertia definition? It is the perpendicular distance from the axis of rotation. So this becomes the perpendicular distance, right? Right. So now what will be this side? Come on, tell me. This is an equilateral triangle. Then equilateral triangle, all sides will be having equal angle 60 degree. If I am not wrong, 60 is 180 degree. So if this is 60 degree, this is 60 degree, this also will be 60 degree. So what is this component of this triangle? Come on, tell me. This is the adjacent side. This is the vertical side. So adjacent side or the base is nothing but what? Cos 60. So this will be what? Cos 60. Got it? So cos 60 will be what? Cos 60 will be 1 by 2. So L will be what? Sorry, A times cos 60 by 2. So this will be M A. Cos 60 will be 1 by 2. So this will be A by 2. Got it? Are you understanding? Have you followed it? Look here, students. This was my triangle. Moment of inertia about this is 0. Moment of inertia from this will be what? Ma square. So if this is 60, this also will be 60. This component will be what? A times cos 60. No. If I take this component, this will be A times sin 60. This is vertical. This is horizontal component. Yes or no? Or the adjacent side. So cos 60 will be what? 1 by 2. So this will be what? A by 2. Got it? So now solve this. Ixx will be what? M into 0 will be 0. Ma square plus ma square ka whole square. This is just not whole square. So this will be what? Ma square by 2 square will be 4. So Ixx will be what? ma square plus ma square by 4. Take the LCM. So this will be what? LCM will be 4 and multiply here 4 ma square plus 1 ma square will be 5 times ma square. So this is moment of inertia of this one. Have you understood? See here students, some of the students would have made mistake. You could have taken this distance. Don't take this distance. The definition itself tells you it is a perpendicular distance from the axis of rotation. So if any problem, if you are getting from moment of inertia, don't panic. You have to just see where is the mass and where is the perpendicular that axis. From that distance you have to take and just multiply m with your r. Sometimes r value will be not given. Directly or indirectly you need to take it. Got it? Have you understood? Okay. So now we are going to study the conservation of angular momentum, a very important concept. So far yesterday, I think in the previous class we had studied what exactly is the angular momentum. So today we are going to study conservation of angular momentum. A very easy concept, but very important from knowledge point of view and application practical point of view. The conservation of angular momentum. All of you know what is angular momentum. Momentum of a body, of a rotating body, is called as angular momentum. All of you know momentum is the quantity of motion. So we know conservation of linear momentum. I had told you ki you should study and come whenever you attend this class, right? I don't know how many of you have studied, but what exactly is conservation of linear momentum? If two or more bodies collide with each other, then the momentum before collision is equal to momentum after collision. What does it imply? The net momentum of an isolated system is always constant. Yes or no? If linear momentum is constant, why not angular momentum should be constant? So here also angular momentum will be constant, but let us understand how. Now again let us compare with our linear motion with rotational motion. Right? Now if net external force acting on a body is 0, what is the momentum of that body? Then momentum will be what? dp by dt. Change in momentum will be 0. This way the momentum is conserved, right? Momentum is conserved. Got it? Suppose there is a body of certain mass of 10 kilogram and on that body net force is not acting. Net force, the total force acting on that body is 0. Which force I am considering? The external force. Look here, I have written external force. If external force acting on that body is 0, will its momentum will change? No, its momentum will not change. Its momentum will remain conserved. No doubt the internal forces may have a role to play, but I am talking about external force. External force acting on that body is 0. That implies the momentum of the system is conserved or momentum of the system is constant. Similarly, here is it valid to take this force? No, here it is always convenient to take torque. If net external torque acting on the body is 0, then a change in angular momentum is 0. Therefore, angular momentum is conserved. Angular momentum is conserved. So what does it mean? If net external torque acting on the body, if net external torque acting on a rotating body, if it is 0, then in that case the momentum of that body, which momentum? Angular momentum of that body is conserved. A very important statement. Okay, change in angular momentum will be constant, conserved. Got it? Have you understood this? Okay. So always remember L will be constant if net external force acting on that body will be constant or 0. Got it? Now, same thing, the momentum before collision or momentum after collision, if you take the total momentum, it will be always constant. Now let us understand little bit of analogy here with compared to this. We know F is equal to ma. Now so far it is clear, right? I will not write that again. Now, how can I write torque here? R cross F. How can I write torque again here? I into alpha. Is it okay? How can I write momentum here? I into omega. Can I write this? Please understand here. See here, torque is rotational force. F is equal to ma. here P is equal to mv. Please understand this. This both the definition, it is very important to understand. F is equal to ma, torque is equal to I alpha. Whatever role mass is playing here, same role is played by I here. Are you understanding? Got it? Suppose I'll give an example. This is our merry-go-round. Okay, it has certain seats here, and there is one more merry-go-round here. Seats here. This all seats are occupied by the children, small children, they have occupied, right? And this is empty. I ask you both, I'll take one random person and ask you, ki apply force on this body. So when you apply force on this body, since it is pivoted by this axis, this body will start rotating. Yes or no? Obviously, it is clear ki this boy will always prefer to push here rather than this, because here lot of people are there, mass will be added more, so he will find always difficult to push this merry-go-round. Why? Because its I is more, moment of inertia is more. So please understand, whatever role mass is playing in a linear motion, same role is played by moment of inertia in angular motion or rotational motion. Are you understanding? So moment of inertia of this merry-go-round will be always more compared to this, because the distance here is almost same, r and r, but here m is more, right? Every time the m is more. So please don't get confused. Whatever role I is playing, that is same role played by m in linear motion. So have you understood this? So now let us exactly understand how this angular momentum is conserved. One thing is clear, if net external torque acting on that body is 0, definitely the angular momentum is conserved. Now you know torque, you know I equals to what? mr square. This is moment of inertia. And what is L? I omega. Always convenient to show an arrow mark. L, angular momentum. If I write P, mv, m के बदले क्या आया? I. Okay. Now, please understand this. Suppose there is one boy, a weird kind of boy. Okay, these are his legs. Don't laugh at the drawing. Please understand the concept. Okay. Now there is a boy. We'll assume that this is the axis, and there are mass kept here. He's just hanging by taking those mass m, and that boy is rotating. He is having a rotational motion. Understand this. What he does is, after one rotation, just he takes one rotation, he brings his hands closer to him. What change are going to take place? He is going to rotate very fast. Later, for the third round, again he opens. Then again he rotates very slowly. Third, fourth time, again he closes. Again he rotates very fast. How does it happen? See here, this is conservation of angular momentum. Please understand. First thing, what he is doing? He is extending his arms. Speed is slow. He is closing his arms. Speed increases. Again extends. Speed decreases. Again closes. Speed increases. This is what exactly happens. Now let us understand why it happens. Okay. Now see here. The distance has increased. So here mass has increased. Mass has increased. The distance has increased. R. So definitely I will increase. Moment of inertia will be increased, right? Compared to this first case. So in first case, what is happening? I is increasing. He is extending his arms. Once he extends his arms, the moment of inertia increases. What is moment of inertia? mr square. The distance is more. mr square will be more. So in this case, I will be more. So omega will be less. How does it see? Understand. If I take I from this, I will be what? L omega. So in first case, I is more, omega is less. So this is increasing, this is decreasing. Then this will not change. This will remain constant as it is. In second case, what happens? Second case, he just closes his arms. So once he closes his arms, this I will decrease. Why? Because R will become 0. R will become 0, right? It is bringing his arms closer, closer and closer. The R becomes 0. So once R becomes 0, the moment of inertia will become 0. In this case, moment of inertia is decreased and its angular velocity will increase. So this is becoming less, this is becoming more. There is no change in angular momentum. Angular momentum is remaining constant. In third case, again he extends his arms. When he extends his arms, moment of inertia increases. As a result, omega decreases and L remains constant. This is what called as conservation of angular momentum. This is called as conservation of angular momentum. Suppose in first case, moment of inertia was 10 kilogram meter square. So omega will be what? 5 radian per second. In second case, it will become 5 kilogram meter square. So this will increase 10 kilogram meter per second. So now apply in that formula. In first case, you apply L omega. This will be I equals to first case 10 L omega. Omega is how much? 5. So 10 into 5 will be what? 50. Angular momentum is conserved. In second case, again you apply 5 L and 10. Again 10 into 5 will be what? 50. So in every time you are going to get constant angular momentum. This is called as conservation of angular momentum. Have you understood? Okay. Now the conservation of angular momentum is very useful, particularly in sports, right? Suppose, have you seen a diver? Not a driver, a diver, a swimming pool diver. So what he does, you might have seen in the Olympic Games also. He needs to jump from certain height, and while jumping he needs to rotate his body. So in order to rotate his body, you might have observed that he just encloses his body very tightly. He just don't jump this way. While jumping, he will take care that he is making his distance as much close as possible. By doing that, what he is doing? He is decreasing moment of inertia, and what is that? The angular velocity is increasing. Right? Are you understanding? See here, suppose this is the swimming pool, and there is one person, a diver, who wants to jump. So what he does, while jumping, he encloses his body. Right? Don't mind for bad drawing. Okay. So please look here. Don't mind for the drawing. Okay, I'm not a good drawer. Now see here, students, what exactly he is doing when he jumps. See, the person who rotates more, he is going to get that gold medal, right? So what the diver does is he encloses his body as much as possible. He squeezes his body. So once he squeezes his body, what he is doing is he is decreasing that R. And once he decreases that R decreases means I also will decrease. And if I decrease, omega will increase. So by that time, he is getting more chance to, he will rotate very fast. He will rotate very fast. And the more he rotates, the more chances he will get a gold medal. Are you understanding? So the conservation, so what is happening here is the conservation of angular momentum. You might have seen in acrobats or in this in the Olympic Games only, or in the ballet dancers, what they do is they try to enclose their body as much as possible, so they can rotate very fast, and when they extend their arms, then they rotate very smoothly. Got it? So there are wide applications of conservation of angular momentum. So in the next class, we will study a concept of moment of inertia, how to find for different bodies. Okay, and I want you to do one homework for this. In the comment section, you should tell me where you are using the conservation of angular momentum in your day-to-day life. Okay, I expect everyone to write that into a comment section. Okay, how you use conservation of angular momentum in your day-to-day life. Got it? Okay, one small thing is remaining, that is couple. So this is called as conservation of angular momentum. So last concept, just a definition, then we'll stop. Couple is a pair of equal and opposite forces with different lines of action acting on a body is called couple. Just remember the definition. They'll not ask anything more complicated from this topic. So So couple is nothing but a pair of equal and opposite forces with the different lines of action acting on a body is called as couple. Now couple will give rise to again rotational motion. Let us apply that definition in your day-to-day life. Like if I want to open this marker, what I do is I cannot marker by just by giving certain orders. Ki open the marker. No. When I need to open this marker, I need to apply the force. Now how do I apply the force? I need to take my two fingers, one thumb and one index finger, and I rotate it, or I just pull it. I just rotate it. So when I'm rotating it, how force I'm applying, you see, there is one force applied by this finger and there is one more force applied by the thumb. So this finger, the direction is in this and thumb is opposite to it. Magnitude will be same because it's my own hand, right? So when I rotate it, this rotational effect is called as couple. Couple is nothing but a pair of two equal but opposite forces. Here, opposite forces. See, this finger is in this direction, thumb is coming backwards. A pair of equal and opposite forces with different lines of action. The line of action of this finger is in this direction, whereas thumb is opposite to me, acting on a body. Which body? This body is called as what? Couple. Got it? Is called as what? Couple. Have you understood? Okay, usually they show couple this way. If there is one more force F1 here, there is one more force F2 here, then the resultant is given by this. Got it? So usually they show R1 of this and R2 of this. Got it? Have you understood? Okay, so we'll meet in the next class. I hope you understood. Okay, and please write in the comment section ki how you use angular momentum in your day-to-day life. What are the other applications of the angular momentum? So till then, bye bye.